We are going to talk today about topographic maps and the way they represent things, like terrains or different things that have a complex geometry, but also roofs. In this case, you can also see that there are contour lines that define a terrain in a simple way. But if you have seen this exposition about the human body, there was a body cut up in slices to define something very complex, and it's used also for animation with Rhino and in 3D printing as well. Is those kind of multiple slices that define a body like this. So every horizontal section would have a contour like this. It's the same system, 3D printing, as you can see. So the basics are, it's a way to represent points. So every point is represented according to a plane. The reference plane should be this one. Naming A, and the elevation measurement it has from this distance from the plane till the point in perpendicular. Okay, so point A should be this. As this is below, this should be point B minus 8.81, and when we see a topography like this, and if we represent a point here and we say like this is the 0, 0 point, well, in this case we don't have point, but we could put like this is my 0, 0 point. If my house is elevated from the terrain, let's say 1 meter, and this is my house, we will put here a text saying this is point A plus 1 meter, and this should be point 0, and if we have another floor, maybe it's plus 3.5, because if the height is 2.5 or 2.80 from floor to floor, let's say. But I will explain that if you're talking about sections. In this case, in topographic design, every contour line is set with this number. This number corresponds as if there was a line joining all the points in the same height. So if we make a line joining this point, that point, and that point, this line would be the contour line called 1.22. In this case, this is a professional topographic map. You can see that this is there's a difference in 3.5 meters. So that means that in between there are 3.5 meters. So this is half a meter, more or less, right? And the same here. So that will be 862, 861.5, and 861, 860.5, and 860, right? And this line, of course, 860.5. So normally we make cross sections from this to simplify. I have that terrain in 3D if you want to have a look. because I move every contour line, I move it up half a meter, and I told SketchUp to make this 3D plan more or less to see how is my terrain, but we have to make sections like this. This is like in 3D. In this case, we can see how I move these contour lines up to make this terrain. You cannot see anything here, but if you go to see the final plan, what is it? Here. So this is the final plan with the section and the house in it, where you see this is like a section from the terrain down through this section line. So the way we do this is, with this image I can explain it. So you have all these contour lines, and you know that everyone is divided unit. What I saw you was 0.5 meters, but if it's an urban planning, maybe it's every 10 meters or 100 meters or 1 meter, 1 unit. And you have to just make perpendicular lines, and that would be the section through this point. In this case, you can show it again, like every level is represented in different colors. You see here that you have 500 meters, and the difference in the contour lines. Okay, so how we do this? There are different things we have to know. Is like the first thing is like when you represent a line in this system, as I told you, is the point, and in between brackets you have the distance, and this is like, imagine this is a line, like this line represented in this system. There's a slope, right? And because this is a slope, imagine that line I show you should be something like that, right? Where we have that there are -1, -2, and point A should be here, like more or less this distance 2.5 below this reference plan, and 1 up. So if we want to know this slope or this angle, this is like if we make we turn in 3D this line. So this is the unity we go up, in this case 1 meter, and this is what is called the module in between, that is going to make the difference. It's like the x, and this is the y. Y is equal 1, and this is what we need to know to calculate the slope. We can apply the tails, so we know that x to the square plus y to the square equals this distance, so we can have the true length of this. And in this case, it's other way to represent the slope, in this case 2/3, and if we divide 2 by 2 is 1, and we make one line here, so the module, like in this case I show you, is 1.5, because this is 1 meter, this is the slope 2/3, so the module is 1.5. I'm going to use it, this after all. And most of the times we have the law that is telling us the slope for our roofs, for the roofs of our houses, and sometimes it's 10%, also for the slopes in the streets. 10% means that every 10 units, 1 is up. What is the same? Every 100 units, 10 goes up. So this is a slope 10%. is the same as this 50%. So every 100 units, 50 is up. So this is a slope of 50%. So what if we have to, we learned how to make a cross section in topography, and now we are going to represent the slope in a roof. Imagine we have our house like this. If we have this slope, if the line is in the middle, both slopes are the same, right? So this is just one line in the middle. If I move that line to one side, you can see that this slope is higher and this slope is different from that one, and we have to calculate it. And we can also have a roof like this, and the problem can tell us this is a 30% is a slope roof, this is 35%, and this is maybe 32%, let's say. Imagine we have to put solar panels here and we have to calculate for the best angle to have the all the solar rays and all the heat the sun can give us. So, and here maybe there's the maximum slope we can have according to the law. This is like everyday life. So we will go here, and this is the roof of our house. Sorry, I had solved it. I have solved the problem there. And imagine we have something like this, okay? Oh, sorry, this was not working because I need one line here. No, this is it. Camera up. So imagine we need to draw a roof like this. And let's do first if all the slopes are the same. If all the slopes are the same, we just have to draw a line 45 degrees from here, mirror, mirror again here, and we can just copy this because if all the corners and all the surfaces have the same slope, all these lines are exactly 45 degrees. That's it. We just have to continue the lines, and that will be our roof. If we do it here, let's say that will be something like this. I need it right in the middle in this case. And this is what we have done. More or less different proportion, of course, and the intersection line would be those lines, okay? So this is roughly what we have done. What if the slopes are different? If the slopes are different, let's say in this case, I'm going to do it again, sorry. Imagine this part is 2/3 this part is, let's say the slope is 2/3 and this part is 45. Let's remain this as it is. The only thing that will change is like that face and that face, it's 2/3. So we go here, we just put like here 3, here 2. This is the slope. This is like we turn it down. That will be the slope. But what we need to calculate is the module. The module is the x, remember. I'm going to separate it so you don't get confused. And every meter, every single meter, I will have this distance, right? I'll change the color. This distance is the distance I have to make parallel line to this line. Okay, I know this is 1.5 meters because I have calculated it before, but you can see it here, 1.5. So I just copy this 1.5. And because this is 45 degrees, that means that every one is up 1. So this is the slope, 45 degrees, of course. So here the x is 1 instead of 1.5. So parallel to this line, I have to put 1, right? And same parallel to this line, 1. If I join that point and that point, I have the new roof. If I join that one and that one, that will be the new shape of my roof. And here it could have other slope, but it will be the same system. And this is all that you have to know about this system and topographic maps.